Please, Mamsurova, who will talk about transboundary extremal lengths. Please.
Okay, so thank you for organization. It's a pleasure to be talking here, Ivan. And sorry, I don't have fancy slides as Leo, but I will try to explain what's going on in Odet's Schramm article, which is called Transboundary Extremal Length. Actually, it's like the first paper where this notion is presented. But I will start with some motivation, then some maybe elementary reminders. I guess, yes, that's not that I guess. Schramm already said a few words about it yesterday. And also there are some intersections with his talk and talk of Melkana and even a bit Leo's talk. So we will start with the definition of conformal equivalence of two domains. This is, we can generalize it to higher dimensions. In general, like conformal maps that are just maps preserving angles, but we are restricted to a very special case of domains in a complex plane or even sphere. So for us, we will call two sets conformally equivalent if they are biholomorphic. And what does biholomorphic mean? It means just that there is a holomorphic bijection such that its inverse is holomorphic too. Okay, so it's a condition to preserve angles. We can think about like preserving angles between x and y axis. There are a lot of ways to think about it. And also we can say that it's exactly the same thing that say that our function is bijective, holomorphic, and with non-zero derivative. That was also mentioned by Schramm yesterday. Okay, so for us, two domain of Riemann sphere or complex plane will be conformally equivalent if there is a homomorphic between them. Okay, I will do some more elementary, like well-known but very important things. The important example of conformal maps is Möbius transformation. I'm sure you already saw it. So we are taking a point Z and we are mapping it to AZ plus B over CZ plus D, where AD minus BC is non-zero. So if you want, you can see this transformation as an action of linear group over the complex plane or sphere, and yes, and also if you want, you can extend this map to infinity in the case of Riemann sphere. There is a very particular example which Leo showed us yesterday. It's example of Möbius transformation mapping an upper half plane to a unit circle. In Leo context, it was to say something about different hyperbolic space models. But yes, sometimes for us, it will be just more comfortable to work with half plane and or a disk. So we can change these two models between them. And I want to show this picture here. We can see that, yes, it's not like it's an exercise to show that it's really mapping a half plane to a unit disk, but what is important is that right angles are moved to right angles. It's not a real proof, it's just a big demonstration of this conformality of this transformation. Okay, now I want just to say a few words about automorphisms. For me, automorphism, it's just mapping to itself which preserves the conform structure. So it's just a biholomorphism to itself. And we have three nice spaces, interesting for us. That's unit disk, which is the same as a half plane, complex plane, sorry, and the Riemann sphere. Okay, why are these three so important? Because there is a uniformization theorem that says that every simply connected domain with Riemann structure is conformally equivalent to one of them. Okay, so we can, with knowing Möbius transformations, we can classify all automorphisms of these three model spaces. They all are given by some Möbius transformation. The exact form is not very important. We're just stating some conditions on the coefficients. It's just practical to know that it exists. Okay, now we are moving to the uniformization theorems, like unit disk or half plane or complex plane. They are very nice domains, and it's in general they are highly symmetric. So usually we would like to prove some geometric properties to these domains and show maybe that they are conformally equivalent, that they are invariant by conformal mappings. So the question is which sets we can normalize to this nice form, or in general we can ask ourselves which domains of the complex plane or Riemann sphere are conformally equivalent. Once again, Schramm already talked about it a bit. There is famous Riemann mapping theorem that every simply connected, so without holes in a complex plane, is conformally equivalent to unit disk. I guess that Riemann proved this theorem in the case where the domain is bounded by Jordan curve, and then it was generalized by there was a whole industry around them. In particular, it says us that two simply connected subsets, which are not complex plane, are always informally equivalent one to another, because they are both equivalent to a unit disk. Okay, so we saw that the topological disk
is simply connected. Not connected, yes, but simply connected.
Yes.
What is simply connected?
Without holes. Yes. You can is a domain where you can
No, the connected not first.
when you can take a loop and shrink it to even density.
We can also use connect the convex subsets of, or it is not defined for a complex plane. There exists definition of convex subsets of.
Yes, I guess it's like the same with SNR2, but I'm not sure that I understand your question. Could you just? I don't understand your question, sorry.
We know what is a convex set, for example, in Euclidean space.
Yes.
And here, I don't know what we can define, but also convex subsets.
Yes, we can just explain SR2. And then we can define convex sets. And any convex set will be simply connected, but there are some simply connected spaces which are not convex, something like that. Okay. Also, Schramm talked a bit about what happens with annulus. It was a case of like it was in the part when we talked about modulus, and it was today in Melkan's presentation too. So like all domains which are topologically anomalous is conformally anomalous with some known inner and outer radius or a punctured disk. And I hope we will see the idea of demonstration later if time permits. So, and I guess Denise will, I don't know who is Denise, and is he here or not?
A bit later, he will come a bit later.
Okay, I know that he will talk about it too.
Yeah, we did it on purpose, so we will
Okay.
continue.
And yes, so what do we have? We have simply connected domains, which are the same thing as unit disk. We have domains with a hole, which is the same thing than another with some radius or a punctured disk. So it seems that boundaries everywhere there are circles or points, and it motivates the following conjecture of Hilbert. Firstly, I will say what is the circle domain in complex plane or sphere of Riemann. It's just a domain such that boundary consists of points or circles disjoint between them. So the famous conjecture is that every domain of Riemann sphere is conformally equivalent to a circle domain. And this is nice because we suppose that it's easier to work with circle domains. Some historical setting, it was conjectured by Kerber, and he proved it for finite case, for the case when I have finitely many boundary components. I will call it finitely connected, yes, finitely connected case. And then for almost 80 years, it was open as conjecture for infinite number of boundary components. It was demonstrated in 1993 by He and Schramm, I don't know how to pronounce He, for domains with countably many boundary components. Then, 2 years later, Schramm showed the simple, demonstration of this theorem, introducing transboundary extremal length. And in general case, the conjecture is still open. So, okay, I will use notation CD for conformally equivalent to a circle domain. And from here, I will have some like very dense slides, but I don't want you to read everything what is written on slide. It's more that you could read it after if you are interested. So, okay, we would like, what is Schramm's strategy? It's to approximate somehow the countable case to finite case. So we have a strange domain, something like that, for example. And we have infinitely many boundary components. The question is how we can approximate it to a finite case when the Kolbe conjecture is known to be true. For this, we will need some technical theorem, which is in fact the main theorem of the paper, as for me. first of all, I want to, it's just for the future, I want to complexify these domains somehow. And how can I do it? What can I do? I can shrink all complementary components to one point. I say just, we don't have colors for a blackboard. If not, it's not a problem.
But we have several blacks.
Thank you. Okay, so I want to say, for example, that I can somehow shrink, just identify all points in this complementary component to one between them. Okay, so we have this identification with quotient topology, but basically we just shrink everything what was in complementary in a connected component of complementary to one point. And what are we trying to do? Like, it's a small speculation, but we're trying to forget the geometry of these poles, and we want to somehow count them anyway. So we want to translate geometrical data to combinatorial data. So this complexification, it will preserve only combinatorial data. Okay? Yes?
And what is what's this object, like what structure does it have? Like, is it just a set or is it something else or something with?
Please, it's a topological space.
Okay. Yes.
You don't have complex structure anymore, but you have no, I will.
Is it discrete topological set?
No.
Okay, but is it like?
Imagine you just you have a sphere. I will do a. Imagine it's not discrete. Imagine that you had a sphere and you had some domain here that you shrink to one point. Topologically, it's still a sphere. And well, it's not evident, but if you did it, if you did it countably many times, it will be still a sphere topologically.
Yeah, I mean, if you do it on the sphere and then
She started she started with the sphere.
You started from sphere?
Yes.
Yes.
I started from sphere. Yes, for me, c'est chapeau is for even sphere. C'est chapeau. Yes,
So
so.
can we come to a consensus about the question? Or what is it?
It's a sphere.
It's a sphere.
My question is, does it have like a complex structure?
No.
With singularities at the shrinks, like something like this?
No.
Like,
No.
okay, that's not
To connect it, maybe it's good.
okay. Thank you.
Can I ask you a
What?
question?
Yeah, sure.
I don't understand why isn't the initial space compact
Is the same.
Which one?
before the factoring?
Well, I mean, what depends on you actually
Oh,
or before structure.
I'm sorry, I don't understand which one you're talking about.
so what you're doing this transformation to compactify the space, right?
Oh, I call it compactification, but it's, well,
It's not compact.
it's compact in the same
Initially-
sense as Riemann sphere, but we can do the same for plane and then it will not be compact. It's no, yes, it's called compactification, but
Okay.
actually it's not. Thank you, it's a good question. Okay, so we will use later the fact that we can see a curve into Riemann sphere as a curve into this factor space, because we just shrink a part of a curve which was inside shrink space, shrink domain to one point. Okay, and this is my notation for the pre-image of a point pair via this factorization. Okay, so if pair was the normal component, that is just a point. Normal component, I mean, it wasn't, it's not corresponding to the complementary component. And it was, if it was in a complementary component, the preimage is just something. Okay, so I will say a bit about Curtadori kernel convergence theorem in normal setting. Normal setting, I mean, when we, well, not applied to this problem. So what we have? We have that sometimes, and even usually, conformal maps are extremely nice for taking limits. Usually we can normalize somehow everything and then choose a sequence, choose a subsequence, sorry, of original sequence which converge to something on compacts. And it's not the same limit for different subsequences. And also, like this limit, if it's not constant, it's conformal. Moreover, it says who is the image of this limit mapping. I will just read now what is written. It is the connected component of the complement of a Hausdorff limit of something. If you are interested, I can define Hausdorff limit of subsets later, but the idea is really that we have limit mapping, and we know where what is the image of this limit mapping. Okay. Now the problem is that it gives some information about the image of space before the factorization, before we shrinked what wasn't in our domain, but no, it doesn't give a lot of information about the image of the domain we shrinked. So for this, for this, Olden Schramm developed a new version of Curtadori kernel theorem, the so-called extended Curtadori kernel convergence. And for this, I will define some notions. So yes, the idea, we have a set in complex plane, something like that. Now we can ask ourselves, what is it, how can we compare area with diameter? Should it be that diameter is very, very big and area is very small as we want? Or it couldn't happen. For this, we define so-called fat sets. The definition is, I will just draw the definition because it's
It's on the board.
oh, thank you.
We can consider domain without interior points, and then in this case, if we have larger diameter, the corresponding area equal to 0.
Not with simply connectedness in that case.
It is on Euclidean space. Oh, it's not in a
Could you
computer.
repeat your example, please?
If we have a domain without interior points, for example, is
Be simply connect.
That she's trying to do the opposite of.
It is not,
She's trying to define fat sets. not
yes,
sets.
yes, okay, it is not, example.
Yes, I am going to talk about fat sets, not about thin sets, right? In general, I just want to say that my set can't contain cusps. That's the idea. That's forbidden. Because the definition, what happens, like we want to say that if we have our set R, we can choose any point and look at some wall around this point such that it doesn't contain R entirely. And we want that this part of intersection would be not too small compared to the area of this circle. So actually, we can't have example like Rome because we can take a point somewhere here, take a radius, take a ball of smaller and smaller radius, and then we have some angle inside, which starts to be thinner and thinner. So the part of area occupied is smaller and smaller. And okay, Buffet domain is just complementary complement of Fed domain. So yeah, one more example. This is not a Fed domain. This is a Fed domain. And this is nice because it shows that there are Fed domains who are not quasi-disks. Okay. So yes, we can show the disk fed, how they are fed, and also what is Cafet sets are very nicely uniformizable. So it's a good thing to say. I can explain it during coffee break. Yes, also fatness is invariant after Möbius transform, and we can even see what happens with the constant of fatness if we wish. And it's also invariant by conform transformations.
So can you go to the previous? So disks are 1/4 fat. Can you give an example of something that is
Yes.
more fat?
I will
Better.
draw what does it mean. We can take a disk.
Mhm.
Now I choose a point very close to its boundary, and I want to look at a domain which is almost containing my disk.
Mhm.
Here, like we have two circles, radius are different in 2 times. So the occupied area of this big domain is 1/4.
So my question is, what is better than this?
Nothing.
So the
Nothing.
okay, great.
Yes, yes. Okay. Now, finally, I will say why are we interested in cafetness. It's because usually it provides us some isoperimetric inequalities. And also, there are some nice properties which are known for finitely connected domains, but we can rewrite it to cofet domains. Okay, now the next theorem, the extended Cartadori theorem.
You can write at least one isoperimetric inequality. What is in complex?
So there's maybe so I think that the circle is lattice is somehow related to a form of isoperimetric inequality. Like how would you prove that the circle is lattice?
Yes, good question. I would say that
Mhm.
okay, I can trust.
My question is nicer, not
Clear?
to prove, but is this somehow related to isoperimetric? If you say yes, perhaps.
Just say it.
Yes, no, it's like it's exactly the question How I forgot the name, but it's exactly the same that to ask which figure have the biggest square with fixed perimeter.
Isoperimetric.
Yes, but there is also a name, a particular name for this problem. Like there was a beautiful
yes.
legend about Greek queen. Well, yes. So, yes. Answer is yes.
Okay, great.
Any other questions?
Maybe one.
Yes.
So if you have any figure with this constant width, is it the same or not? Like this real triangle or something?
I didn't. Sorry.
Like if you have I don't know, a figure which has constant width, does it mean that it's as flat as circle? No.
What do you mean by constant width?
Like it's a real triangle.
No,
No, like
because you can have a.
not just triangle, triangle, a real triangle, the one which has like so you want to squeeze between two parallel lines and
But you always have angles. If I understand what you, the condition will be break, and when we choose a point close to the angle.
So probably not, because one thing you can do, if you want a cusp of work,
Okay.
right? You can have many cusps so that when you squeeze it with the same width, and that would be not that big. Yeah.
Yes.
So the after the Mobius transform, the tau star is not precise anymore, right? Or is it?
After Mobius transform, it is. After quasi-conformally,
Wait, so it's precisely tau over 200 if F is connected. Where does the 200 come from?
it's just like infinite estimations for. Yes, if you want like a method to prove that Möbius transformation is to show, to say to yourself that, well, Möbius transformations, there are actually linear maps and inversions, and then you're looking what is going on for inversions and for translations, and then you are just doing triangular inequality.
Oh, okay. And somehow you get.
There are too many questions.
So this number is
That's a very nice
example.
Imagine I start with the tau by set, and I get my into 200 by set,
Yes.
and then I can come back by another Mobius transformation, and this the first one become a tau over 4000.
Yes, but okay, if you are tau fat, then for every
No.
tau prime who is smaller, Q is also fat.
Okay.
Yes, it's a nice example to show that it's not optimal constant, but for now we don't care about constants. Yes.
Did you say that this is 1/4 flat?
Yes.
Yes.
Yes, and
Why?
it's like there is.
Here is the half and
Is it, why is it 1/4?
It means that if we take, like, we have a disk, when we choose the point inside the disks, and now we took a neighborhood of this point such that disk original one is not entirely in this neighborhood. And we look which part of
Yeah.
air of this neighborhood is occupied by disk,
Yes.
by intersection with disk. And here is like an example how to approach the 1/4. You're taking a disk, you're taking a point close to the boundary, and then you're doing disk with almost 2 times more grand diameter.
What I was thinking is this 1/4 product theorem.
I see what.
I don't know.
Maybe, but I don't think so. But
But if I can add one comment, when you say that this is quasi formally varied, I think you should be careful. Because you can. Okay, you can
Yes, fatness is, I don't know if it's your remark, but fatness is conformally invariant, but the constant is not conformally invariant.
Well, but also, I think what you mean probably, it's quasi-conformal or conformally invariant if you're considering mappings of the whole plane or the sphere, because you can map any domain to any other simply connected domain in particular to a non-factor.
Yes.
So that's why it's important to say it's globally quasi-conformally invariant.
Thank you. Yes.
So if it's a conformal mapping of the whole,
Of the whole, then it's a
then
model.
it's,
But if it's conformal of the domain, we can map.
I mean,
to
pretty much,
which
yeah.
the examples we have with the slit, so.
Okay.
I will, here I need to accelerate. So I will just say that fatness gives us a good condition to generalize Pythagorean theorem. So now, what is going on here? We have some conditions, and if we will discuss the conditions later. If these conditions satisfied, then we can extend a limit of some subsequence of our original sequence of mappings, and we will see which is important for us is that we can the limit mapping, it doesn't think it doesn't do like bad things on the complementary components. It can't explode the point into a circle, and it can't shrink a circle to a point. This is what important for us. This is what we want to know about the complementary components. Now, a few words about the conditions. So, domain is cofet, sequence of conformal maps, they converges to some conformal map, and then for every element of this, yes, for every element of this, for every function from this sequence, we want to have a domain such that it contains domain we study. For example, we can imagine that we study this domain. So as the n, we can take domain itself, or domain with closed one hole, or domain with closed second hole. So we can do something like that. We want to have countable number of holes in general, and also we want to know how to extend the function fn, which is defined over there, to a function fn tip, which is defined on the n. Okay, then we can describe where we have convergence, what is the image, but once again, very important that when we look what happens with the complementary components, F can't shrink big complementary component, and it can't explode small complementary component. Okay, I don't have enough time to explain how it helps to pass to from finite to infinite version of Köbel's theorem for infinite countable version. It's written in my slides. I try to do it understandable. But in general, what this theorem shows, it shows how to approximate our strange domain by finite domains, the n, domains with which are finitely connected. Okay, now I will skip the demonstration, And I will just say a few words about the demonstration of Cortador's theorem in this extended setting. The article actually is called Transboundary extremal length, and we didn't talk about extremal length like at all. Maybe I will not have enough time to do a link, but I want just to say that this is like how to say it? This is a generalization of like a known method in conformal theory. So I will just say very rapidly what is extremal length. So we have a curve or a family of curves, and we want to understand, for example, in some domain, and we want to understand what happens to this curve when we conformally map domain somewhere. The problem is that the length of curve is not invariant under conformal matrix. You can preserve the conform structure, but change the length of this curve. So we should define length as follows. Rho, if you wish, it's a way to describe all metrics compatible with the conform structure. And it's the same, we can define area of a domain. Now we can ask ourselves, we have a domain, we have some set of curves in this domain. How length of this curve, how it is connected with the area? And the answer is exactly the quotient between these two is called exactly extremal length. So yes, idea it is at which point area is comparable with diameter for different metrics possibles. And yes, the question, like for pository, does the part which is incursive is similar with something we saw? Okay, we already like had this idea at which point area and diameter are connected when we talked about flat sets. So,
Circles are kind of the largest backsets.
yes, yes, yes. And also, yesterday Grant was talking about conform modulus, it's called, or just modulus.
What's my notion of modulus? Okay, but sure.
Yes, I wanted just to say that the invariant for conformal transformations, what Grant talked about yesterday, it's like the same invariant, just normalized.
It's 1/8.
Yes, just normalized differently. Okay. And also there is a way to, so we saw that it's, and well, we saw it's conformally equivalent. We can count it sometimes, for example, for annulus. And the method which Schramm used is to generalize it somehow to the case when our curves can pass through the domains which are not from the parts which are not in our domain. So I will just say how we constructed our compactification. Yes, we shrinked everything which was in complement of, we shrinked every connected component of complement to one point, Now we would like to define measure on it. Before we had the big measure to measure the area, and we had a metric induced by Euclidean metric to the length. And here I will just add some combinatorial data. This was the length for us before, so just integral of by all possible metrics along the curve. Now we will add what happens in our shrinked components. We will add some point mass. The same for measure. We had the big measure, and then for complexified space, we can just give measure 1 to all points to which we shrink our connected component. Then transboundary is calculated as transboundary extremal length is calculated as extremal length.
What is mu?
What is mu? Now we can do.
You have the big measure, now you are.
Yes. What is mu? We added we have a domain with connected components, which with some we have had a domain and we shrink some points. I will just say that I add there are measure everywhere at each point. We added. Here I will stop with definitions and with talk in general, just few ideas. What is, yes, the question you didn't ask, but I will answer it. What is new here? We know now we collect also the data of what's going on when curves leave our chosen domain. So if we had a domain with a hole, for example, before we couldn't say something for curve like that. And now for transboundary extremal length, we can say something from this curve or family of curves like that. It is something which is now I will do a small speculation, but somehow the big idea of what is that is similar with the definition of fat and cofat sets. And that's for it that we get the condition of cofatness in extended version of Cartadori theorem. And yes, Cartadori theorem is just a direct way to prove Löb's conjecture in infinitely connected case. Sorry, I think I didn't say half of what I wanted, but I should stop.
One question, can I understand correctly with transboundary? So if you cannot count module of that curves in the curve path through this domain, that is through the complementary of the domain, because it just doesn't count, because this curve is not in your domain. And if you shrink it, then you have a point, and then if your curve goes through that point.
Yes, it's exactly that.
Something, and then it will be the module. Okay, great. Okay.
Oh, and also one.
Yeah, because it's going through the complement domain, so that this down cannot be counted. But you want to count.
I think this is kind of also related to what how gave
Yes, I wanted to say it.
comments of
With the case of kind of strange.
Talk. Oh, listen twice became more understandable.
Yeah, I have a question. This might be a stupid question, but in the Cortis conjecture, there is no restrictions on the being fat or cofat. But in the the generalized Cartesian theory,
There is.
Yes,
there
that's
is. How do
true.
we get?
But yes, it's because we In this demonstration, there are a lot of steps before you can actually
Oh,
use Pythagoras theorem. At some point, we will have domains which are cofed and which approximate our domain.
Oh, so you approximate any sets by cofacts, the sets that you shrink, you approximate them by cofact sets and.
Yes. Yes.
Okay.
And even by cofacts, yes, and then yes.
Okay.
Can I ask a comment to the question? Answer their question, right? So what Ina was describing, one of the theorems Schramm proved is uniformization of cofact sets. So, but in general, this previous term, the case that all countably connected sets boundaries don't have to be cofact. So that's a different theorem. In particular, it doesn't apply in the case of all countable sets because one consequence of Irina mentioned that in this extended current theorem, it had the property that non-point boundary components have to go to non-point boundary components and vice versa. Remember yesterday I had two examples, the one with splits and one with classes. The classes, they are not cofact, but Ryan and she actually proved, well, some other people proved that they can replace cofact things, but the things which are lines, they are not cofact. So in particular, that theorem fails in that example. That's why the point can blow up onto a circle in that example. But in the case of classes, this theorem, the generalization of this theorem still holds. So you actually get that the point goes to point. That's like very much related to what you're saying. So you can't really approximate an arbitrary domain with cofact, and that's kind of a big thing of current research. How much further can you push?
And what is the current sufficient condition? I mean.
Well, yeah, so there will be maybe a talk about that. The next talk is about that, I think.
Okay.
What's the current state of affairs? I think, yeah.
I mean, yeah, so if I understood it correctly, the classes can be approximated with cofact set.
They kind of are, not exactly, but the splits cannot.
Okay,
The
so.
splits cannot.
The splits
classes
cannot,
kind
but
of, they
graphic-
are essentially that. Whatever